Let us solve this problem by using the Thomas algorithm. In this case, we have the Ax equal to B, where your A is the system matrix here, and your X is the temperature, and your B is the output matrix. In this case, you have the tridiagonal system, therefore we can choose the Thomas algorithm because it is the most efficient algorithm compared to GE and also LU. In the first step, we need to find the LU decomposition from this matrix. This is the region that we need to perform the forward elimination. So 2.04 is your pivot element, therefore we remain. In the second row, we need to make -1 here become 0. This can be done by using the factor. The factor that you need in the second row is E1, where your E1 is equal to -1 divided by 2.04. By using the forward elimination at the second row, then you should get -1 equal to 0, which is this. Take the 2.04 minus with the -1 multiply with the factor E1, then you should be able to obtain 1.5498. So this is your F2. Then we continue with the row 3 here. To make -1 equal to 0, we need the factor E2, where your E2 is equal to -1 divided by this component. So we cannot use 2.04 because it has been changed to 1.5498, which is the F2. So you take -1 divided by your F2. And you should get this answer for E2. Then you continue to take the row 3 minus row 2, multiply with the factor E2, then -1 will become 0, and 2.04 minus with -1, multiply with the E2, then you should be able to obtain 1.3. So after perform the forward elimination at the row 3, then you obtain your F3 equal to 1.3948. By using the same procedure, we can continue with our row 4, and to make -1 become 0, we need the factor E3. E3 is equal to -1 divided by this component. Since this component is changed to your F3 already, so your F3 is 1.3948. So -1 divided by F3, you should obtain -0.7169. Then you continue to take the forward elimination at this element by using this equation. So take the row 4 2.04 minus with row 3 -1, and then multiply with E3. You get the F4 answer to be 1.3231. So you can substitute F4 to be this answer. Since we only perform the forward elimination at the diagonal and the lower diagonal here, the upper diagonal doesn't change. So you have the same value at the upper diagonal here. With that, you can see that the U matrix is actually the result after you perform the forward elimination at this region. And what is your lower triangular matrix here? So this is where you apply the factor. So you have your E1, E2, E3 factor that can be obtained from here. You can substitute inside. And then don't forget, you need to put 1 at the diagonal. So this is your lower matrix L. In summary, if you have a tridiagonal matrix like this one, we can find the LU decomposition from it easily by perform the forward elimination in this region only. So you start from first row. Since row 1 is pivot equation, the 2.04 doesn't change. Therefore, you obtain your F1 equal to 2.04 here. Then you continue with the second row here. To make -1 equal to 0, you need the factor E1, which is -1 divided by 2.04. And then you can find the F2, which is the forward elimination result for your 2.04 by using this equation. And you should obtain this answer for your E1 and F2. Then you continue with the row 3 at these two elements. To make -1 become 0, you need the factor E2, and E2 is equal to -1 divided by this component. You need to be careful, this component has changed to F2, so you have to take -1 divided by F2 for your E2. So this is the answer. And then you continue to take the forward elimination for 2.04 here by using this equation. So after you perform this equation, you should obtain your F3 equal to this answer. Therefore, you can substitute inside. And you perform the last step on the last row. Take the forward elimination for these two components. By using the same procedure, to make -1 here become 0, you need the factor E3. So E3 is equal to -1 divided by your F3. So with that, you obtain this answer for your E3. Take the forward elimination on 2.04 here by using this equation. You should be able to obtain the F4 equal to 1.3. So you can substitute all the F here from F1 to F4 into this formula, and then substitute all the E factor from E1 to E3 into here. So for the lower matrix, make sure you have 1 at the diagonal, and for the upper matrix, so at the upper diagonal here, it should be equal to the original equation here. To check if your L and U matrix are accurate, you can multiply between these two matrices to obtain the LU, and it should be equal to your system matrix A. So if this equation is valid, then we say your LU decomposition is successful. Once you find your L and U matrix from your system matrix A, then we can proceed for the forward substitution using this formula, and then we perform the backward substitution using this formula. First of all, your output matrix B is this, so we can substitute inside. And for the forward substitution, you need to start from the first row to obtain your D1. So we have done this many times, so you should obtain 40.8, and then you continue for the second row to obtain the answer for D2, and so on, to obtain the D3 and D4. So this is the answer. After you obtain the D matrix, you can substitute inside the second equation here. So now you are going to find your solution temperature. So we can start from the last row in the backward substitution to obtain your T4. So please recall that in the parabolic PDE, we are using this notation where you should know T represents the temperature. 4 here means that the position or the location for your X position, let's say X4, and 1 here means the time at time 1. So it means the temperature at position X4 at time 1. Then you can continue with the last second row and so on to find your temperature at point 3, point 2, and point 1. So you should get this answer. Lastly, you can verify your solution and check the accuracy by substituting inside the original equation. If left hand side is equal to the right hand side, then we say this answer is accurate. Let's try with more example. So this is your example 2, and we take this example from the previous problem in the parabolic PDE chapter. So far, you have learned the Gaussian elimination, LU decomposition, Gauss, Seidel, and also the Thomas algorithm to solve the inverse problem. So based on the system matrix, you can see that you have a band matrix that has a lot of zero outside the bandwidth. Therefore, we do not prefer to use the Gaussian elimination and LU decomposition here due to the efficiency problem. Gauss-Seidel is suitable to solve the band matrix. If we continue to check the detail for this band matrix, you found that the bandwidth is equal to 3. So we can say that this is a tridiagonal matrix. Therefore, we do not choose the Gauss-Seidel because Thomas method is well known in solving the tridiagonal matrix, where this method provides the most efficient algorithm to solve it. We are comparing these methods in terms of efficiency, which means those who have high efficient algorithm can compute the things faster. In terms of accuracy, all of them have comparable accuracy. You should understand now why we choose the Thomas algorithm to solve this problem instead of the other method. In this case, we have the matrix AT equal to B, where you have the A matrix, which is the system matrix, equal to this. And in the first step, we are going to perform the LU decomposition of this tridiagonal matrix. And we only perform the forward elimination in this region only. So for your upper matrix here, you can see this region remains. And for the lower matrix, you have 1 at the diagonal. So what you need to do is, you have to find what is the E1, E2, E3, as well as F1 to F4. We start with the first row, where you have 1.04 to be your pivot element. Therefore, your F1 remains equal to this number. For the row 2, we perform the forward elimination in these two elements. So for the first element, to make it 0, we need the factor E1. So E1 is equal to this. After you compute it, we substitute inside this equation, take the row 2 minus with the pivot row 1, multiply with the E1. Then you obtain your F2, which is this answer. We continue with the third row. So to make this element 0, we need the factor E2, where E2 is equal to negative 0.02 divided by this component. So this component in the second row here, it has been forward eliminated to F2. So you take negative 0.02 divided by F2, you obtain the E2. And then you substitute inside this equation. So row 3 minus with your pivot row 2, multiply with the E2. Then you obtain your F3 here. Lastly, you perform the forward elimination on these two elements. To make the first element 0, you need the factor E3. Using the same procedure, E3 is equal to negative 0.02 divided by F3, which is this. Then you substitute inside this equation and take the row 4 minus with row 3, multiply with the factor E3. Then we can change this element into F4. With that, we success to obtain your L and U matrix. You should aware that the decomposition for the L and U matrix that we use in the Thomas algorithm is similar but not exactly the same like the LU decomposition using the Gaussian elimination method. So previously in the LU decomposition method, to make this element here 0, you need to perform the forward elimination on these 3 rows. So all the elements here will be performed the forward elimination. Then you obtain 0 at these 3 elements, and then prime here indicate the change of the value after the first forward elimination. Then you need to continue to make these 2 elements here to become 0. You need to perform the forward elimination at these 2 rows on all the elements. Double prime here indicates that these are the elements that you need to perform the forward elimination twice. Then you can see that we success to obtain 0 for these 2 elements. We proceed for this element. To make this 0, we need to perform the forward elimination here at the last row. Then you should be able to obtain 0 at this element. So this will be the result for your upper matrix by using the LU decomposition using the Gaussian elimination approach. And the factor that you use to make this component 0 will be the factor in your L matrix. With that, you can also find your lower matrix. On the other hand, the Thomas algorithm has a more efficient algorithm to find the L and U matrix, because it only performs the forward elimination on very few elements here. So you can see that we just need to perform the forward elimination on, let's say, 1, 2, 3, 4, 5, 6. 6 elements to find these 2 answers. So this is very fast and very efficient. Once you find the L and U matrix from your system matrix A, then you can perform the forward and backward substitution by using these two equations. We have discussed these two procedures before. So to find your D1, we start with the row 1, then you should be able to obtain your D1 answer. Then you continue with the second row to obtain D2, and then continue, you can obtain the D3 and D4 answer. For the backward substitution, you need to start from the last row, and you obtain your T41 answer to be this, and you continue for the last second row, then you obtain T31, and if you continue, you obtain the T21 and T11. So this is the answer for the temperature at 4 locations at time 1. In the previous problem of the parabolic PDE chapter, we obtained this finite difference equation at T2. If you compare the finite difference equation at T1, then you will see the left-hand side here, your system matrix A remain unchanged. Your output vector here changed to a new right-hand side vector. If your system matrix A is remain unchanged, then your L matrix and also the U matrix will be remain the same as well. Therefore, you can skip the step 1 and directly continue with the forward substitution in the step 2. Substitute your new right-hand side function into the V vector here and then compute for the D. And then after you compute the D vector, you substitute inside the second equation here to compute the temperature vector. So this is the answer for the temperature at 4 points, x1, x2, x3, x4 at T2. You should see that we can obtain the new temperature by using the substitution only. So this is very efficient because we do not need the step 1 in order to compute the forward elimination result. In the example 4, we are going to show you that how if you insist to use the Thomas algorithm to apply on a matrix that is not a tridiagonal matrix. It is not straightforward to do this, as we need to make the element here and element here equal to 0. So in this case, you have the tridiagonal matrix with the bandwidth equal to 3. Then you can apply the Thomas method on this tridiagonal matrix in order to solve the unknown x. And then in your mind, Thomas method cannot apply on the matrix which is not tridiagonal. You can perform the forward elimination to convert the matrix from non-tridiagonal into tridiagonal matrix. First of all, the element within bandwidth equal to 3 will be remain, and then we have to make the other element become 0. So we start with 3, 1 here. So by applying the forward elimination using these two equations, we can make these two equations change, and you can see the first two elements become 0 now. You can continue for the second forward elimination to make 6 become 0 by taking the equation 4 minus with the pivot equation 3 and then multiply with the factor. Then you should be able to obtain this answer. Then you continue to make 5, 4 elements here become 0, like this one. So we can use these two equations, where you take the first equation minus with the pivot equation 4 and multiply with the factor. So same procedure for the equation 2, then you can get this. And then lastly, perform the last forward elimination to make 7 here become 0 by using this equation. With that, you success to obtain the tridiagonal matrix. Next, you can continue with the Thomas algorithm in order to solve the unknown x. Normally, for this kind of problem, we will not choose Thomas algorithm. As you can see, you have to convert to the tridiagonal matrix that involve a lot of forward elimination. So this is time consuming. Therefore, for this kind of problem, we would prefer to apply the Gaussian elimination or the LU decomposition. But if you insist to apply the Thomas algorithm, you still can do so. You need to learn how to apply the forward elimination so that you obtain the tridiagonal matrix, and therefore only you can apply the Thomas algorithm.